Hey everyone, and welcome to this explainer. If you're a med or neuroscience student grinding away for your upcoming exams, well, you are exactly where you need to be. Today, we're mapping out human memory systems. And I absolutely love diving into this material because we get to see exactly how modern brain imaging proves, and honestly, sometimes completely upends, what we originally thought we knew about memory. We're going to break down these incredibly complex neural networks into clear, highly testable concepts. So grab your coffee, get your notes ready, and let's map out the brain.
Here's our quick roadmap for today. 1. Overview validating amnesia with neuroimaging. 2. Episodic memory, encoding and retrieval. 3. Semantic memory, knowledge retrieval. 4. Procedural memory, motor learning. And finally, 5. Implicit memory, perceptual priming.
All right, let's jump straight into Section 1. Overview, validating amnesia with neuroimaging. Let's establish exactly how our modern scanning tools build right on top of classical medical knowledge.
So for decades, literally everything we knew about memory came from lesion studies. We're talking about amnesic patients who had suffered really severe brain damage. Imagine that classic clinical scenario you've read about 100 times. A patient sustains profound damage to their medial temporal lobe. Suddenly, boom, they have severe anterograde amnesia. They can't form new conscious memories to save their life. And yet their older distant memories, perfectly intact. Well, over the past decade or so, functional brain imaging, things like PET scans and fMRI, has given us the superpower to look at normal, healthy brains working in real time. And what we're finding beautifully confirms the central role of that medial temporal lobe. But, it's also extending our understanding in some incredibly provocative, really unexpected ways.
Okay, let's look at this biological division, because this contrast right here, this frames the major foundation you absolutely need to nail for your exams. On one side, we have explicit memory. This is your conscious retrieval. When you actively try to remember, say, what you had for breakfast this morning, you are firing up the hippocampus and the medial temporal lobe. But on the other side, we have implicit memory. This is unconscious learning, and it's driven by completely different structures, like the motor cortex, the basal ganglia, and the occipital lobe. The absolute biggest takeaway you can get from this is that these two systems operate completely, 100% independently of one another.
Moving right along to Section 2, episodic memory, encoding and retrieval.
Now, what is really brilliant about James Haxby's methodology in this area is how his team managed to isolate specific brain activity. They used a PET scanner, which, remember, measures sustained regional cerebral blood flow, and they broke face processing down into 3 very distinct separate tasks. Step 1, remember or encode a completely new face. Step 2, recognize a face you've already seen. And Step 3, just do a basic perceptual analysis. Look at 2 faces side by side and just compare them. By separating out these steps, the researchers could track the exact blood flow triggered by local neuronal activity for every specific phase of memory.
And here are the high-yield findings you definitely need to memorize. First off, the right hippocampus was activated only during the encoding of the face. When it came time to actually recognize the face, the retrieval phase, the hippocampus went totally quiet, which is amazing because this perfectly matches the clinical amnesic patient data. Furthermore, encoding activated the left prefrontal cortex, while recognition activated the right prefrontal cortex. That is a massive hemispheric asymmetry. To build on this, researchers like Anthony Wagner used event-related fMRI to track individual test items. Now, unlike PET, which measures sustained blood flow over several minutes, this specific fMRI technique lets researchers track rapid, item-specific responses in real time. They prove that if you see a larger response in the prefrontal and medial temporal regions during encoding, you can successfully predict that the subject will remember that item later. It's like the brain literally lights up more when a memory is successfully sticking.
So the absolutely crucial point here is this definition, HERA, hemispheric encoding retrieval asymmetry. Jot this down, star it, highlight it, because it is a classic high-yield exam question. The HERA model states that encoding involves the left hemisphere much more than the right, and retrieval involves the right hemisphere much more than the left. And keep in mind, both of these distinct processes rely really heavily on the dorsolateral prefrontal cortex.
Let's shift gears to Section 3, Semantic Memory, Knowledge Retrieval. This is all about how we encode and retrieve pure factual knowledge.
Before we look at the specific networks, I just want to draw your attention to Brodmann's areas 44 and 45. Now, you might already recognize these as part of Broca's area, which is traditionally associated with speech production. Well, surprise, it turns out they actually play a massive role in semantic memory too.
Just notice the stark contrast between these two memory types. When you retrieve semantic knowledge like hard facts or really domain-specific information like the difference between animate and inanimate objects, you use your left prefrontal cortex, specifically Broca's area and the ventrolateral region. But remember what we just talked about. While episodic retrieval goes to the right dorsolateral prefrontal cortex, semantic retrieval lateralizes strictly to the left prefrontal cortex. And amazingly, this lateralization to the left stays exactly the same whether you're trying to remember spoken words or trying to remember visual objects.
Moving on to Section 4, Procedural Memory, Motor Learning. We are officially crossing over that great divide into implicit memory.
Think back to our classic amnesic patient from earlier. If you give them a really complex sequence of buttons to push every single day, they will have absolute zero explicit memory of ever doing the task before. They will literally introduce themselves to you as if meeting you for the very first time every single day. And yet, if you watch their hands, their fingers will get faster. They'll make fewer mistakes on that button sequence each time they try it. This is incredibly powerful evidence that implicit motor learning functions completely independently of conscious explicit knowledge. But the big question is, where exactly is this happening in the brain?
Well, researcher Scott Grafton investigated this using what is called a dual task condition. Basically, they deliberately distracted normal subjects to completely prevent them from explicitly noticing the motor sequence they were actually learning. Sneaky, right? By taking the conscious brain completely out of the equation, the PET scans were able to reveal the hidden implicit network. The left motor cortex, the supplementary motor area, and crucially, the bilateral putamen and the basal ganglia all lit up. So when your body is unconsciously learning a physical task, it relies entirely on brain areas that control limb movements, totally and completely bypassing the hippocampus.
And finally, we arrive at Section 5, Implicit Memory, Perceptual Priming. This is our last implicit memory system for today.
Here is another massive definition for your flashcards, the PRS, or Perceptual Representation System. This is the distinct neural machinery responsible for perceptual priming. If you are exposed to a visual stimulus, you are going to process it faster the next time you see it, and this happens entirely unconsciously. And just like the procedural memory we just talked about, it operates without any help whatsoever from your explicit hippocampus-dependent memory systems.
To really understand how the PRS works, I need you to zero in on Brodmann's Area 19. This is the bilateral occipital cortex, basically the visual processing center right at the back of your brain. Researcher Daniel Schachter ran a truly fascinating PET study looking precisely at this area during visual priming tasks.
Let's see how this builds into quite literally one of the most counterintuitive findings in all of cognitive neuroscience. Subjects were shown words and they demonstrated clear, measurable, behavioral implicit priming. Now, as expected, the hippocampus showed absolutely zero activation. It just wasn't involved at all. But what actually happened in Area 19? The blood flow didn't increase. Actually, scratch that, it actively decreased. The deactivation of the visual cortex is what actually correlates with the priming. The brain becomes so unbelievably efficient at recognizing the previously seen word that it literally requires less blood flow and less neural effort to process it. It's working smarter, not harder. So, to put the whole shebang together and summarize our overarching narrative today, neuroimaging has profoundly, beautifully confirmed what cognitive research and amnesia studies suggested all along. The explicit recollection of information, where your hippocampus encodes new info and retrieves recent info, is subserved by a completely separate brain system than our implicit memory, which relies on entirely distinct motor and perceptual neural pathways, like the basal ganglia and the occipital cortex.
I want to leave you with a bit of a mind-bender to ponder as you review your notes tonight. If implicit learning, like perceptual priming, actually relies on a decrease in visual cortex blood flow, what other seemingly quiet brain deactivations might be secretly driving our subconscious behaviors right now? Brain imaging isn't just about finding out what lights up. Sometimes the real secret is finding out what powers down. Good luck with your studies, keep mapping those networks, and thank you so much for joining me for this explainer.